continue with Module 2, we have sequential logic. The behavior of a sequential logic circuit depends not only on its inputs, like this one, but also the information stored inside the circuit. So there are different important types of memory elements for a sequential logic circuit. One thing in this figure, you have your combinational circuit here with the inputs, and the memory elements will feed back and go as an input to the combinational circuit. Whatever is information stored here will be fed as an input, and by then we'll get our output. So some of the important types of memory elements, we have the clock, a device with no inputs and an output that changes from one logic level to the other. Its most important characteristic is its frequency, that is measured in hertz, or a clock period. A clock is often used to synchronize the operation of a sequential circuit. Many components of such circuits are arranged so that their internal states change only on receipt of a clock pulse. Some components are said to be synchronous. So this is an example of a block diagram which uses clock pulses. So clock pulses is fed into our memory element or a flip-flop, and that output of that is fed as an input to our combinational circuit together with the other inputs to get our output. This is an example of a clock pulse timing diagram. Another important part is a flip-flop. As I have mentioned, this is a device that has two different states. There are various types of which depend on how the state is changed. A flip-flop is a two-state memory circuit with precise timing control. The memory elements are used to retain logic values in a digital circuit. The basic memory element is the SR flip-flop. There are many other flip-flops like a D flip-flop or a JK flip-flop or a T flip-flop. So for this SR flip-flop, normally both inputs of the flip-flops are 0. If a logic is momentarily applied to the S input, the output Q will go to the value 1. Because of the feedback of Q into the bottom OR gate, Q will remain 1 even after the S input returns to 0. The output Q can be reset to 0 by momentarily applying as a 1 to the R input. So this flip-flop can be used to store 1 bit of information. Another important type is we have register. This is a set of flip-flops treated as a single unit, like all loaded or stands at the same time. A register can be regarded as a hardware implementation of a word. Example, 16 flip-flops form a 16-bit register that can hold 16-bit number. Another type is counter, a register with some logic attached to make it count in binary. It has a clear input, which sets the contents to 0 when activated, and a count input, which adds 1 to the contents when activated. There are several data outputs containing the value of the counter. Another one are shift registers. A register with logic attached so that the contents can be sampled 1 bit at a time. It has a clock input, which shifts the contents 1 bit position when activated. So here are some things that you need to think about. Some self-assessment question explaining the difference between a sequential logic and a combinational logic, and also explain how the memory of a computer can be implemented in the hardware. Moving on, we have Boolean algebra. All logic operations in digital circuits depend on either the existence or absence of a signal. A variable may have only one of two possible values. Reduced to a two-valued system, both the operations and analysis of digital circuits are greatly simplified. The mathematics of two-valued logic is called Boolean algebra. So we will present here the basic postulates and theorems of Boolean algebra. In the theorems and postulates, we assume a positive logic like low logic level is 0 and high logic level is 1. Before we proceed, take note that a postulate is a statement, also known as an axiom, which is taken to be true without proof, while theorem is a proposition or statement in math that can be proved and has already been proven true. So we have here a few of the postulates and theorems in Boolean algebra. What you need to do is to be very familiar with these postulates and theorems and be able to practice in different problem solvings of this one, just to make you be very familiar of these postulates and theorems. There are also laws of Boolean algebra. We have here some laws of identity, a commutative law, associative laws, idempotent laws, distributive laws, laws of absorption, laws of expansion, and De Morgan's laws. So take note that these laws are already proven to be true relative to Boolean algebra. Some also are here also common identities of Boolean algebra. So we have to take note that the dot symbol may be omitted in some logic expressions. So most of this omission would mean an AND logic. Okay, so these are different identities. When you encounter these type of expressions or terms or equations, then they are proven to be identity and they are proven to be true in Boolean algebra. So we have here an example. So these applications of postulates and theorems and identities can be given in the simplification of a complicated logic expression. Just like this one, this expression here we have is just equivalent to 1. Applying the different laws, different factoring and identities and postulates, then you will come up such that this equation here or expression is just completely equal to 1. Another simplification example, we have here this expression, A ANDed with A or B, ORed with A bar or B ANDed with B. So in this expression, you can see clearly that you can have distributive law over it. So when you're going to distribute A here, you will have these terms, and B here, you will have also this term. Now applying theorem number 5, which is this one, so you will get AA as A and another theorem 5 for BB. So you get this expression. Now factoring, we say factoring, we are going to extract A here. So we have 1 plus B plus this one. We did not do anything about it. Then applying theorem number 10, because we know that 1 plus A is just 1. So you will have this expression. 1 plus B is just 1. Then here, we also have theorem number 3 for A dot 1, which is A. So all this on this after factoring, you get just A. Now proceeding with this term here, we factor out, then apply theorem number 10 and theorem number 3. Then we end up with the result of A or B, or A plus B from this complicated function or expression. So how is this applied? When you are going to draw the logic circuit for this, instead of drawing this expression, you can have this, and the result is just the same. So logic expressions and logic circuits, moving on, we have here can be presented, these expressions can be presented into a logic circuit. That's why you have the AND gates, the OR gates. This is where these are applicable. But this logic circuit is constructed from logic expression. So normally when you have a logic expression, you can create the logic circuit, or vice versa. You can, if you have the logic circuit, you can generate the Boolean expression. So practically, when you are going to generate a logic circuit from a logic expression, it has to be simplified so that there is less gates used, and also the circuit will be simplified. Now, before you draw a logic circuit, we have to take note of operator precedence, such that when you are going to draw something from the expression, you have to draw first what is inside the parentheses, then the inverts or the NOT gates, then the and then you or. In other words, expressions inside parentheses must be evaluated before all other operations. Then the next operation that holds precedence is the complement, then follows the and finally the or. So let's say this expression, the one that we have simplified previously. So we have here this, which is equal to a plus b. We have already solved that one. So looking at it, how are we going to implement this? With the operator precedence, it says draw first what is inside the parenthesis. So we are going to have first the A or B. Now here is A or B, this one. Then it is, the output of that is ANDed with A, this one. The output of this is ANDed with A. That's why we have this. The output of A or B, A or B is ANDed with A. So the output of that later is ORed, okay, with this expression or term. So for this term, we have not A. So A, not A. The output of not A is ORed with B. There. For this term. And then it is ANDed with B. So the output of that is ANDed with B. And the output of those different terms is ORed to get that output. Now what about this one, A or B? So you see the difference? This whole expression is just equal to this. If you're going to have that logic circuit, this whole complicated circuit is just equal to this. So how simple is that? So that means you will have less on economics, and also you will have a simpler circuit when you are going to implement. That is the value of, or the importance of, simplification of a certain expression before you generate the logic circuit. So here is another self-assessment question. You try to prove the identity, this one. But I think we have already solved this one. But you can check again on your own. This one is another identity. You try to draw the logic circuit, practice, okay? And this one is the truth table, another. You're going to have the logic circuit implementation. By the way, if you are given the truth table, all you have to do is check on this one, the output that is one. Thank you.